very pleased to be able to introduce our lecturer, Paul Hoffman, who is going to talk to us about the mathematician Paul Erdos. Hoffman first met Erdos in 1986 and interviewed him over the last 10 years of his life, even following him on his mathematical sojourns. Hoffman's 1987 profile of Erdos in the Atlantic Monthly won the National Magazine Award for feature writing, the most prestigious award in American magazine publishing. In their criterion, the judges proclaimed it a minor classic written with amazing clarity and wit. Then, after Erdos had died in 1996, Hoffman wrote a biography of him entitled The Man Who Loved Only Numbers, published by the Fourth Estate, and for this he was awarded the 1999 Aventis Prize for Science Books. Until recently, Hoffman was publisher of Encyclopaedia Britannica and editor-in-chief of Discover magazine. An experienced broadcaster, he is the author of 10 books, including Archimedes' Revenge, and is currently writing his 11th, The Wings of Madness, about the history of flying machines before the Wright brothers. We both live in Woodstock. He lives in Woodstock, New York, and I live in Woodstock, Oxford. So, Paul Hoffman.
Thank you very much. I hope you're a kind audience. I'm a little under the weather today. I've actually had the flu. So this could be the most eventful talk that you've ever seen, but luckily there's a door for me to run out if there's any problems. I love old things. I wrote about a man who was quite old, and I'll come to that in a moment. So it's wonderful to be at one of the most respected and oldest institutions in the world. I've been slowly moving back in time. I ran Encyclopaedia Britannica, which was formed just down the road in Edinburgh in 1768. And then I became a member of the American Academy of Arts and Sciences. That dates to 1760. And then I got an old barn in Woodstock, New York, which I converted into a house, and it's 250 years old, so that goes back a little further. Now I'm back to 1660, and it's wonderful. Just a few things about Britannica that you might be very amused about. In the 1768 edition, it's 3 volumes. The first is A to B, the next is C to D, and then it goes E to Z. That's because they realized it would take them until now to finish it if they were doing it at the pace that they've gone. And it has wonderful entries. You look up California and it says, an island in the West Indies, perhaps. In the second edition that was done in 1777, you look up, there's no mention anywhere in it of the American Revolution. The closest it comes is under the entry in Philadelphia, and it says, the problem with the American states is the euphemism for it. So it's a delightful book on a reflection of our times. You look up the entry in the first edition for man, and it runs quite long. You look up the entry for woman, and it says partner of man, 3 words. But as some of my colleagues pointed out, at least it said partner. Could have said servant or something else. So maybe we have progressed in some respects. I'm a writer by profession, and the kind of people I write about are those that are passionate about whatever they do. I've written about chess players who spend 20 hours a day behind a board. I've written about biologists who spend all day in the lab trying to find what one gene does. And those are the kind of people I like, who do things to excess. And a friend of mine, Ron Graham, who was the chief of mathematics at AT&T Bell Labs, knew about my passion for passionate people and said to me, Paul, you've got to write the story of the mathematician Paul Erdős. He's someone who's very passionate about what he does. He's getting on in years, and if you don't tell his story, he may pass away before someone has a chance to interview him. This was back in the mid-1980s. So I said, fine, I'd like to meet the guy. So I went to Ron. Ron didn't tell me much about him other than that he was an eminent mathematician. So I went to Ron's house in New Jersey to meet him, and I met a man who was stooped over, who had white hair jutting out from his sides, who was dressed in a kind of pajama suit, and I extended my hand to greet him, and he didn't extend his hand back. He wouldn't shake hands with people. He barely noticed that I was there, and after about a minute he said, when did you arrive? So I looked at my watch, And Ron tapped me on the shoulder and said, "No, he's asking when you were born." And this started my getting used to the fact that I had to pick up an entire language. And he was a man, he was the Bob Hope of mathematics, spouting aphorisms all the time. Mathematicians are machines for turning coffee into theorems, he'd say. He was very obsessed with old age, and he'd say there are 3 signs of senility. The first sign is that a man forgets his theorems. The second sign is that he forgets to zip up. The third sign is that he forgets to zip down. Well, Paul Erdős never achieved any of these signs of senility. He went on doing mathematics to the age of 83, proving that mathematics is not just a young man's game. So I got more and more fascinated. I couldn't understand everything he was saying because he spoke in a special language that was all his own that I had to get used to. He called women bosses. He called men slaves. If you were married, he said you were captured. If you were divorced, he said you were liberated. If you were giving a lecture like I'm giving now, he would say you were preaching. If someone stopped doing mathematics, he said you died. If someone really died, he said you left. But my favorite word that he had was the SF, short for Supreme Fascist, the #1 guy up there, God. And he was a very absent-minded man, not the SF, Erdős was. And Erdős was very absent-minded. He was always misplacing his Hungarian passport. He was always losing his wallet. He was always losing his glasses, and he would blame this on the SF. He would curse the SF for taking these things from him. But what he held against the Supreme Fascist the most was that he was concealing from Paul the most elegant solutions to the world's mathematical problems. I mean, he believed that the SF is sitting up there in the sky with what he called the book. And each page of the book had the most elegant solution to a mathematical problem. And he believed that it was his mission on Earth and the mission of his fellow mathematical colleagues to reveal the pages in God's book. And when I heard this, it resonated with an experience I had in college about mathematical elegance, and this is what attracted me to math and ultimately to Erdos after I met him. And I was taking a calculus course and was with a rather surly professor who was always seemed to be in a foul mood and never had much time for us. Well, one day he came charging in buoyantly, carrying 2 bottles of champagne in his hands, cracked them open. This was in 1976. It was because the 4-color map theorem had been solved, and he wanted to celebrate it. For those of you who aren't mathematicians, the 4-color map theorem is very simple to describe. The idea is that any map that you draw of countries, no matter how convoluted you make their borders, I mean, you can make a country that's going all sorts of ways, then take out a set of crayons and color each country solidly, 1 color. What's the maximum number of crayons that you need to be able to color any conceivable map such that 2 countries that border on each other don't have the same colors? Well, for 124 years before it was proved in 1976, the answer had thought to be 4. And many of the world's ablest mathematicians had tried to prove this, weren't able to, and many of the world's biggest cranks had tried to find a counterexample. In other words, a map that required 5 colors, but no one could. So finally it was proven, and that's how we had our most enjoyable math class with champagne. Well, the following week we came back, and he was more surly and more depressed and more fidgety than ever. We asked why. And it was because he had learned that the proof had been done by computers. And it's not that a computer did the proof that bothered him. It's that, I mean, he believed it. You know, he thought other people can run the software, they can check it for bugs. That wasn't the issue. The issue was what the computer had done. It had managed to reduce every conceivable set of maps to 1,500. And then it had hand-colored them, spending 1,000 hours doing this. And it demonstrated that. So the problem was not that he didn't think the theorem was true. He believed it was true. But you didn't know why it was true. The proof was too complicated to follow. What mathematical elegance is about is you've got to understand why it's true. I mean, why isn't it 7 colors instead of 4? You can't tell from this proof. And this was the kind of elegance that Paul Erdős stood for. The other thing that he believed, and again, he was always concerned about growing old. Actually, since the age of 4, he worried about it, apparently. And, had all sorts of jokes about old age. And as he got older, he spent more and more hours doing math because he knew he had less time left, and you had to reveal yet another page in God's book. But he believed that mathematics gave him, and anyone who does it, a certain kind of immortality. And I asked, what do you mean by that? And he said, well, it gives you immortality because you are discovering truths that are immortal. I mean, when Euclid, the ancient Greek mathematician, proved more than 2,000 years ago that there's an infinite number of prime numbers. Prime numbers are numbers like 3, 5, 7, 11, 13, 17 that have no divisors, unlike numbers like 4, that's 2 times 2, or 9, that's 3 times 3. So Euclid proved that there's an infinite number of prime numbers. Well, this proof was true not just in his time, it's true today. It's true in any other world that exists. It will be true long after people are gone from the planet. So Erdős said that by finding these immortal truths, you're buying yourself a little bit of immortality yourself by brushing up against it. So I was hooked by my first discussions with him, and I really wanted to follow him around. But I quickly learned how much it was going to be taxing on my stamina. I was in my 30s then. This was, again, in the mid-'80s. He was 73. And that first night I stayed at Ron's house. By the way, he's married to a very great mathematician named Fan Chung, and the two of them do a lot of math together. And the reason why Erdős likes to stay with them is because there are 2 mathematical playmates that he can pester instead of just one. So I watched them do math. It started at lunchtime, and they did it all afternoon, and they sort of worked through dinner on napkins, and this went on. And although they had the evening news on at 11, it went on. And finally, it was about 1 o'clock, and Ron suggested that they should go to bed, and Erdős said, there'll be plenty of time to rest in the grave. So they went on for like another hour, and finally Ron said, we've got to go to bed. So when they went to bed about 2 o'clock, I lay on the couch, thought I'd get a good night's sleep. Well, at about 4:30, I'm waking up because in the kitchen next door, Erdős is banging pots and pans together. He's banging them and banging them and banging them because he wants to wake up one of his 2 mathematical playmates to come down. Finally, Ron comes down, and they do some math, and for a few hours, actually, because they were making great headway on a problem that had been irking them for a long time. But at 8 a.m. in the morning, suddenly Erdős says, I know how to prove such and such theorem. He says, I've got to call this guy in California. Ron points out that it's 5 a.m. in California, since it's 8 in New Jersey, and Erdős says, good, that means he'll be home. So nothing would stand in the way of his search for mathematics. So at that point, I decided that I was going to follow him around. This is a man who had no home. He had no possessions. All his possessions fit into one small suitcase and some plastic bag that he had from some shopping store in Budapest. And part of this briefcase was taken up by a large, old-fashioned dinosaur of a radio. I think it might have had tubes in it, shortwave radio. This was so that he could monitor the world for the downfall of communism, which he'd been doing for many, many years. So this is all he had. I mean, he had no family, he had no wife, he had no kids, he had no sexual relationships with anybody. His entire mission was devoted to mathematics. And he made a circuit of 25 countries. And he would go and show up, often unannounced, on the doorstep of a fellow mathematician. He'd declare, my brain is open, which meant hit me with your most challenging mathematical problem. And then he would stay with you as long as you could entertain him with math problems. As soon as you couldn't, then he moved on. And lucky you had to pay his airfare or train fare to his next destination. He didn't have much of an income, but he would get exorbitant day rates from places like IBM, Thomas Watson Research Center, AT&T, Bell Labs to come and solve problems. The money he didn't care about. He had to hear the problem first. If the problem interested him, he showed up, then he collected his $25,000 for the day, and then he would pay back all his friends who had lent him money because he kept track of how much money people had given him. He was also a sucker for any good cause. I mean, if National Public Radio was having a fund drive, he'd take whatever money he had in his pockets out, give it to you, you're supposed to mail it to them. If you passed, a billboard about a home for wayward girls, he'd immediately want you to write down the phone number and send off a contribution. If he passed a beggar on the street, because I was with him many times and saw this, he'd give him whatever money he had. If it was a quarter, it was a quarter. If he happened to have $50 in his pocket, he gave the guy $50. I mean, in some sense, he was a great, great humanitarian and didn't care anything about material goods. So the question was, now I'm going to follow him around, but how are people going to respond when I show up unannounced too with them is the big question. So Ron decided that he was going to call 100 of his closest collaborators, who would be the people he'd be most likely to show up, because I was going to follow him around for a full month so I could absorb what he was doing. Paul has a lot of collaborators. I mean, this is one of the things that distinguish him from other mathematicians. The stereotype, which of course isn't true, but the stereotype of mathematicians is someone who's squirreled away in their study, working long hours, scribbling, and that it's not a social activity. Paul turned it in to a communal social activity and is single-handedly probably responsible for that way that mathematics has become. He had 485 co-authors, 485 papers written with different people. He wrote 1,500 papers in all. And just to give you a sense of that, you can't really measure mathematics in numbers of papers because someone could write one paper that would change the world. But all of these papers were important. None of them were trivial. Some were very significant. It was far more papers than anybody else has written in this century. Even in the last years of his life, he would publish 50 papers a year, which is more than most good mathematicians published in a lifetime. So now that Ron had called a lot of his collaborators, I tagged along, and we started in New Jersey, and I watched him do mathematics. It was absolutely fascinating. He often did it like a way a chess grandmaster plays simultaneous chess, if you've ever seen that. There's a whole bunch of boards set up, and the grandmaster runs from one board to another, pauses for just a few seconds and then moves. This is how he did mathematics. It'd be a circle of people, and he'd go from one to the next, working on each of them with a problem. And it was really good for the mathematicians that weren't quite as swift as Erdős, because it gave you the chance to think about what you were going to say while he went around. It was also good because it exposed mathematicians to what other people were working on. And I saw him do this on numerous occasions, usually at conferences. He might go to one or two talks at a math conference, but then he would end up camping out in someone's hotel room or in the lobby and attracting a whole group of people that would sit around him. But as I struggled to stay up, because at this point he was doing math 20 hours a day, and he had been on, he took amphetamines for years. He had been doing this, but he didn't seem wired at all. I mean, he wasn't a person who was hyper at all, but that kept him up, and I was having trouble with my coffee cups, keeping up with him at this point and jotting down what was happening. And I found that everywhere I went, he talked in, as I said, the Bob Hope of mathematics with these little aphorisms that he was constantly spouting. And he didn't want to take time out to talk to me very much. It wasn't because he objected to my being there. He didn't want to take time out from doing mathematics. That was the principal thing. But every now and again, he'd go for a walk. And it was on these walks where I joined him, where I started to learn his life story, because I was absolutely taken by him. And I learned that he was born in 1913 in Budapest to two mathematicians. They were high school math teachers, which meant they both had PhDs in mathematics. And when his mother was giving birth to him, she had two daughters who were aged 3 and 5, and they contracted scarlet fever while she was in the hospital, and they died the day he was born, her two daughters. Imagine that. She comes home to an empty home without her two kids. And the result of this was that she did not let him go to school and rarely out of the house until after the age of 10, because she was afraid that he would contract a fatal childhood disease, and she wouldn't let him be around other infants for that reason. So he's at home, but then at the age of 1.5, his father is captured by the Russians in a Russian offensive and thrown into a Siberian prisoner of war camp for 6.5 years. So now there's no father from the age of 1.5 on. His mother still has to make a living, so she's off teaching high school math. There was a German governess that was around. There were a lot of math books that were around. And he said he taught himself to read by reading math books, and that he immediately fell in love with numbers at a young age. At the age of 3, that was his first great discovery, he told me. He discovered negative numbers. The idea that if you subtracted 100 from 50, you got minus 50. And when his mom came home from work, he proudly told her this. He also said he told her that was the year he discovered death and that he knew he was going to die, something that's he was obsessed with, as I said, for the whole rest of his life. So his father, to pass the time in this prisoner of war camp, decides to teach himself English from a book. There's nobody in this camp that speaks English, so he teaches himself English from the book. And then when he finally returns home when Paul is 7, he teaches Paul English. So neither of them have ever heard a native speaker speak English, which explains why Erdős's accent was so impossible to follow. I mean, it took me 3 days before I could understand what he's saying. And whenever there have been news footage of him on American TV, and even though he's speaking English, they have subtitles so that you can understand what he's saying. So after the age of 10, he starts to go to school, but every other year, his mother yanked him out of school because she still couldn't decide whether it was safe for him to be in school. They were extremely close. She did everything for him. I mean, she made every meal. She buttered his toast in the morning. He never buttered toast until he was the age of 17. He never tied his shoes until he was 12. I mean, she literally did everything for him. And at the age of 17, this is 1930 now, he went to the University of Budapest, and he graduated in 4 years, both with an undergraduate degree and a PhD. And that's when he did some of his first work on prime numbers. Prime numbers were his closest friends, he told me. And it was in his first year as a college freshman, when he was 17, he came up with a very remarkable proof. It had been proven before, but in a very convoluted way. It certainly wasn't the proof that was in the SF's book. And Erdős replaced this proof with one that went in the SF's book. And it was, the original proof was done by sort of the father of Russian mathematics named Pafnuty Chebyshev. And it's called Chebyshev's theorem. And the idea is that between any number and its double, there has to be a prime number. So if you take the number 4 and double it, it's 8. There has to be a prime number between, at least one prime number between 4 and 8. Sure enough, there's 2 prime numbers, 5 and 7. But he was able to prove this in a very elegant and simple way. And he became, very well known, not just in Hungarian mathematical circles, but around the world at that point. And in fact, it was spread by a little poem that when Chebyshev said it, and I say it again, there is always a prime between n and 2n. People sent out in postcards to their colleagues. So it's now, he graduates, it's 1934. Stuff is getting rough I should backtrack for one moment. After World War I, in 1919, when we had the Russian Revolution, and there the communist regime was in power for decades, obviously. You also had a Bolshevik revolution in Hungary, but there it really failed. The Bolshevik government was only in power for 133 days. It was quickly overthrown by very right-wing folks that instituted the first fascist regime, first fascist post-World War I regime in Europe. Because some of the leaders of the Bolshevik revolution had been Jewish, fascist thugs retaliated by attacking Jews left and right in Budapest. This is responsible for the exodus at that time of many eminent Hungarian mathematicians and scientists. John von Neumann, Edward Teller, Eugene Wigner, people that went to the States and then went to Los Alamos and are responsible for the atomic bomb, all left at about that time. There was a synagogue opposite Erdős's apartment. And if you looked out the window, he could often see, and he's, how old is he now? This is 1919, so he's 6. 6.5 actually, when this happened. And he could see Jews being beat up after they came out of services from the window. And his mother said to him, "We're going to baptize you and make you a Catholic so that you'll be protected, so that you'll be safe, so that you can pretend that you're not Jewish." And he said to his mom, "No, I was born a Jew, I'm going to stay a Jew," which is an incredibly remarkable statement for a 6.5-year-old to show that amount of will. And he was not a religious person throughout his whole life, but he was a very principled person. I mean, he believed in being who you were. I mean, one of the things that I was most impressed by is he got tons of honorary degrees from universities, at least 30 to my count. And if he ever heard that at that university someone was having a tenure struggle, and the nature of the tenure struggle was that they had some kind of unpopular view, he would immediately return the honorary degree. He would never give a speech or talk at that university again. He believed very much in sticking up for individual rights. So in 1934 now, when he has his PhD, things are getting rough in Europe. more and more anti-Jewish legislation is being passed in Hungary. They're limiting the number of Jews that can go into certain professions. They're limiting the number of Jews that can go into universities. Each year, the law changes and the percentage is reduced. So he knew that Hungary was not a great place for him, so he got a postdoctoral fellowship here at Manchester, where he was for 4 years, from 34 to 38. And he would go back and see his mother, who, of course, he was very attached to 3 or 4 times a year. In 38, starting in March, it became unsafe to do that. In March was when the Nazis invaded, when Austria surrendered to the Nazis, which meant that the Third Reich was now within 100 miles of Budapest. Then came September of 38 with the Czech crisis, and Erdős decided that Europe was not a place that he could stay. So he went to the United States, where he went to the Institute for Advanced Study for a year and a half in Princeton. Then for the next 10 years, this was before he did his circuit of 25 countries, he did his circuit of universities all around the United States during those years. In 1944, of all the atrocities in World War II, Churchill said that the greatest atrocity was when the Nazis moved into Budapest, and that was in 1944. In the period of 2.5 months, 500,000 Jews were killed in Budapest. Paul had no news. I mean, mail was cut off to the United States, even though Hitler had invaded Hungary. Hungary was thought to be sympathetic to the Nazis beforehand, so there was no mail, and he didn't know what had happened to his family. It took a few years before he found out. His mother made it through. His father died when the Nazis forced his parents to move to the ghetto, and 4 of his 5 aunts and uncles were killed by the Nazis. After that, he had a problem. As the Cold War started, the United States decided that he must be a Hungarian spy, and Hungary decided, because he had spent so much time in the United States, that he must be an American spy. So neither country would let him in. So at that point, he spent most of his time in Israel that did welcome him, and he went to some other countries in Europe, like Holland at the time. He didn't get back into the United States, believe it or not, until about the time of Kennedy's assassination in the early 60s. They finally lifted the embargo on him. And then he came to the United States permanently. I say permanently because he was a nomad and really didn't have a home, except Ron Graham built an extra bedroom onto his house for him, which was where copies of all his papers were stored. So he probably spent about 2 months a year there between all his travels. At that time, once he came to the United States, his mother started traveling with him. They did everything together. She sat there right next to him when he spoke, even though she couldn't understand a word of English, and most of his lectures were in English. He held her hand every night when they went to bed together. They were inseparable. When his mother died, about 7 years later, that was when he started taking amphetamines very seriously. And that's when he started churning up the number of hours that he was doing mathematics to 20 hours a day. I mean, that's what I observed during the month that I was with him. His eyesight started to fail him, but he didn't want to take time out he needed a cataract operation, and that would have slowed him down. But his friends at the University of Memphis, he had a lot of close collaborators, insisted you have to have a cataract operation or soon you won't be able to see. Finally, they got a suitable donor. It was all arranged, and Erdős sat down with the doctor. Erdős was holding a mathematical paper, reading it most of the time. He was talking to the doctor, but he asked the doctor at one point, will I be able to see? The doctor said, of course, that's the whole point of the operation. And Paul smiled and was beaming. So now they lead him into the operating theater, and he's still carrying this mathematical paper, reading it about up to here, because that's only what his eyesight would allow. And they get in, and they start to dim the lights down, and he has a tantrum. He says to the doctor, but you said I'd be able to see. The doctor said, yes, after the operation. And they said, but you're doing the cataracts operation just on one eye, so can I read with the good eye while you're doing it? At that point, the surgeon didn't know what to do, so he phoned the mathematics department at the University of Memphis and said, can you send over anybody who can talk math with this guy while we put him under with the anesthesia? And sure enough, a few of his colleagues showed up, and that's what they did. In 1996, which was the last year of his life, by the way, he had a heart attack earlier in Budapest, and he was in a hospital for a while, but he continued to do math the whole time. People would visit him, and again, he would do math with 6 or 7 people in the room. The doctor came in to check his blood pressure. one of his colleagues told me he threw the doctor out and said, come back in an hour and a half because we're finishing this important result. But in 1996, he was in March in Boca Raton, Florida, a conference he went to, an annual conference, and he was giving a talk, and when he just got to a point where he was going to end a proof, he fell over, completely passed out. No one knew what had happened. You can imagine everyone's rushing around. Security guards are then trying to evacuate the room and say, get out, get out. He had a wireless mic attached to him like I did, and as people are leaving, you hear him say, no, please don't leave. I have 2 more points to make. That was in March of '96. In June of '96, in Santa Cruz, he was in the audience at a talk. And a mathematician was presenting his work and said, here's a problem I'm stuck on. Paul immediately leaped up. Maybe leaped up is too strong a word for an old man. He got up out of his chair, and he started to complete the proof that this guy had been stuck on. At that point, he fell over and had a heart attack at the conference, and he had to be taken out in an ambulance. 2 days later was when the closing banquet of this conference was, and you can imagine it wasn't exactly a happy occasion. I mean, the conference was mostly, in large part, made up by many of his closest collaborators, and it wasn't a happy time at the banquet. And when everybody's sitting there, suddenly the door opens, and in comes Paul Erdős, arm in arm with his 2 heart surgeons, who had put in a pacemaker. And he thanks the heart surgeons in front of everybody, and then without losing a beat, completes the proof that he was doing. He wanted to die with his bootstraps on. He wanted to die working. And he told me that he most admired the 18th century mathematician Leonhard Euler because he did mathematics up until his deathbed. If anybody did more math than Erdős, it's Euler, who wrote 19 volumes supposedly between the first and second calls to dinner. And in the year, I think it's 1787, when the planet Uranus was discovered, Euler was sitting there. He was an old man at this point. His grandson was on one knee. He had a cigar in his mouth, and there he was calculating the orbit of Uranus. And as he finished calculating the orbit, he said, I die, and fell over, and he was dead. So Erdős told me, I was once telling this story at a conference, much like this one, and somebody jumped up from the back when I got to that point and said, yes, another theorem of Euler's has now been proven. And Erdős said, that's how I want to die, doing mathematics. Well, he almost had his death wish. He was at a geometry conference in Warsaw. He had finished an important proof. He didn't die in front of the audience, but he went back to his hotel room, and he had a heart attack, which left him unable to speak, and he had another heart attack several hours later and died. I mean, in a way, it's very sad, because he was a man that couldn't be alone, who always surrounded himself by people, and that his very last moments that he had to spend alone in a hotel room is kind of sad. His legacies to mathematics I want to talk about just for a moment. He did a lot of work in prime number theory, as I said. He was responsible for nurturing loads of child prodigies. The only thing that he took time out from doing mathematical research to do was to go to elementary schools, even kindergarten schools, occasionally nursery schools, believe it or not, and talk about mathematics. And if a child seemed to perk up and show some interest where the rest of them were just playing and ignoring him, he would go and talk to that child, and then he would meet the child's parents, and then he would find a mathematician in that local community who he could pair the child up with to nurture that mathematical talent. Did this especially with girls, and is responsible for quite a few female mathematicians, despite his vocabulary about bosses and slaves. He was very open-minded. He would do math with anybody. There was a saying that if he got on a train, he'd end up proving a theorem with the conductor. He worked with great mathematicians. He would work with people that hardly knew any mathematics, but if they wanted to talk to him about it, he was certainly game. He has legacies in terms of whole fields of mathematics, which he helped, if not pioneer, really launch. One is called Ramsey theory. This is very appealing to me because it has a neat philosophical underpinning. The idea is that complete disorder is impossible, that there's order to everything if you look deep enough. And I'll give you an example. Carl Sagan, in his show Cosmos, used to say, sometimes people look up at the heavens and they see 7 stars that are almost in a complete row. And they go, that can't be by chance. That must be because aliens put them there as an extraterrestrial trade route to lead us to their civilization. Well, when Erdős heard of that, he would start calculating and say, well, how many stars do you have to throw up there at random before you're guaranteed to find 7 that are almost in a row? These are the kind of problems he did. Or take a sheet of paper, what mathematicians call a plane, and put points on it at random. Okay? How many points do you have to put at random, such that you're guaranteed to find somewhere 3 points that if you connect them to form a triangle, that all sides are equal? Or how many points do you have to put there until you're guaranteed to find 5 points, so that if you connect them, you form a pentagon with all sides equal? He was always trying to find order, and although Ramsey theory is named for Ramsey, who did the first theorem in this, it was really Erdős and his colleagues who put this on the map. It was interesting. It was back in Budapest in the 30s when he was in college, and there was a law against meeting in public parks. Particularly, there was a law against Jewish people meeting anywhere in public. They used to go and meet in a park and prove these theorems and scatter before the police would come. And the group that proved these was called the Anonymous Group, because there was some statue in this park of the first historian of Hungary who was called Anonymous. So they called themselves the Anonymous Group. So Ramsey theory started back in the 30s. That's very important. He did a lot of work in what's called combinatorics that has to do, it's hard to describe, but it's discrete mathematics. It's about counting and classifying objects. It forms the basis of many algorithms or recipes that computers use to solve problems. The irony in this is that Erdős would never use a computer. Okay? He refused to use a computer. Not because he had anything against them, but again, he wanted to see all the steps in a proof so that he didn't want to miss something. It's not that he thought the computer would do something wrong. He was happy to have his friends use computers to check on his own calculations. The other thing that I think he leaves to this world is a lot of great mathematical problems that are unsolved. He put monetary contracts out on problems based on their difficulty. Something would be worth $3, some are worth $3,000. I think there's $25,000 worth of problems out there, and a foundation has, actually an oil man in Texas has offered to match the amount if people solve them, so that there'll still be Erdős papers published in the future, even though he's not around now. And he was the Johnny Appleseed of mathematics. He spread mathematical ideas wherever he went. He knew what your strengths were, so he'd come up with a problem that was just beyond your reach, but one that you'd be able to do. He often knew your abilities better than you did. And in spreading mathematical news, he was much like a medieval monk before there were newspapers who went from one town to another to spread the news. That's what he did within his area of mathematics. And I think the other thing that he certainly did for me is, he showed how important it is to follow your passion, to do whatever you want to do passionately. How many of us are going to be able to go through life and end up doing what we want until the age of 83 and dying happily that we were able to do it? And if you think about this guy's life and what happened to him, in a way you could look at him as, he was an oversized personality. The way you could look at him as a complete weirdo in terms of how he lived his life. And in a way you could look at him as somebody who had overcome so much that would have put somebody else in a mental home. If you think of the fact that he was at home until the age of 10, basically with no parents, that he wasn't allowed out, had very little contact with children, that he had a relationship with his mother where she completely smothered him. There's stories I can't confirm, but they fit in, that they shared the same bed until he went off to college. He had no sexual relationships with anybody, man or woman, he told me. And certainly this was confirmed by his closest friends. He just said he had no interest in that. He formed no real intimate friendships with people other than mathematical ones. Yet he was enormously kind. If he would ask you about your children, if they were sick, he'd want to do something to help. But I think the fact that this guy took these difficulties that he had as a child, and then all the deaths in his family with World War II, and then being homeless because neither Hungary nor the United States would have him and consider him to be a spy, all these things that might have driven other people mad, he took this and channeled this into an activity that made him enormously happy. He was a happy man. He radiated happiness. He wasn't like John Nash, the mathematical economist who was schizophrenic, who was a depressed individual. This is a guy who loved what he did and radiated that. And I think that's what inspired me the most, the fact that he was able to overcome these difficulties that might have done in the rest of us and channel that into something, and then leave a lasting legacy with all these people that he had turned on to mathematics. I mean, his contributions were enormous. Thank you.
Well, thank you very much, Paul.
Thank you.
And we've now got some time for questions. And because we're filming this, we'd like, if anybody wants to ask a question, Imelda will do it, or Joe. They've got microphones to give you so that you can ask the question. And for the record, could you please also, when you ask, before you ask the question, say your name, and then we will have a nice record for the whole thing. Now, anybody want to ask a question? Oh, yes, please. Here's the microphone.
John Guyver. When Paul Erdős asked people, is your mind open? I assume that everyone would have said yes. No one would have said, no, it's closed. So did he ever find anyone else apart from himself that actually had an open mind? Because there are very, very few around.
No, I don't think so. So occasionally people turned him down in doing math. Again, you know, at the 20th hour, some people were just falling asleep. And, you know, he was the house guest from hell. You had to do everything for him, or put it this way, your non-mathematical spouse had to do everything for him. Since he couldn't boil water for tea, he had one change of clothes, which meant you had to do his laundry every day. He couldn't drive, so he would order you to drive him around. So occasionally people got fed up with him, but that was the minority. I mean, he had 485 collaborators because people loved him, and they couldn't wait for him to come. He would save you years off your research, and he would think up all sorts of intriguing problems that would leave you a lifetime of problems to work on.
So even if this was, he had an idea that was quite remote from anything that they thought they might find the solution in, they would listen.
Well, if he was very good about not telling you a problem unless he thought your abilities and your area of math were such that you'd respond to the problem. What would he do if he suddenly had a brainstorm about something else, which he had constantly? He'd grab the phone and call. You'd get huge phone bills after he left. I mean, he'd call everywhere, at all hours, you know, whenever he had something to add to something.
Barry Lewis, of which achievement, mathematical or otherwise, was he most proud?
He was very proud of some work he did jointly on what's called the prime number theorem. And mathematicians in the room know what that is, but for the rest of you, as I said to you, Euclid, the Greek mathematician, proved that there's an infinite number of primes. As you get larger and larger, the primes thin out. It's harder to find them. The prime number theory, it tells you what the density of primes is. In other words, it tells you roughly how many there are in a certain gap, you know, whether it's between, you know, 1 billion and 2 billion or 1 trillion and 2 trillion. This too had been proved before in a rather complicated way, and in joint work he did with a, I think, Swedish or Norwegian mathematician named Selberg, they were able to prove this in a much simpler way. He was very proud of that. It became marred in controversy, though, over which of them contributed the most to it, and so Paul didn't like to talk about it. He had no patience for, I mean, it's interesting in mathematics, the number of priority fights that there are. I mean, unlike physics, where if you discover a particle, you could produce an image from an accelerator, or biology, where you might be able to show something you grew or cultured in a test tube. Mathematics, it's very hard to prove and who did what to whom when, and it just shows the passion of the subject that people have very lively disputes, going back to a man who didn't stand in this room, but in the Royal Society's headquarters back in the 1600s, Isaac Newton and his dispute with Leibniz. There's been a royal tradition of this. Paul had no patience for this, though. He thought it didn't matter who got credit for it. He left his name off all sorts of results. He didn't care. The idea was to knock off another page in God's book. That's all that counted.
Jim Kennedy, I presume that in the early stages of his career, he must have been offered some sort of post with a university.
Yes. I mean, the closest he came to a full-time job was Purdue offered him a sort of part-time teaching job, which he did for just a few days and dropped because what would happen is he'd be lecturing and then he'd come up with a brainstorm and want to call, you know, a mathematician in Hungary, and it became incompatible with the idea of teaching. So he never had a full-time job. He had agreements, like with the University of Memphis, I think for over 15 years. He came there, I think, 2 weeks a year to do math with some of its faculty members, and he delivered a lecture or two that time. So he had a few arrangements like that where he'd appear for a week at a university, but it wasn't conventional teaching. It was working with people and delivering a talk. You know, I should add that in the mathematics world, there's something called an Erdős number. That's a very coveted distinction. If you wrote a paper with Erdos, you have an Erdős number of 1. If you wrote a paper with someone who wrote a paper with Erdos, you have an Erdős number of 2. Einstein has an Erdős number of 2. If you wrote a paper with someone who wrote a paper with someone who wrote a paper with Erdos, you have an Erdős number of 3. The highest known Erdős number is 8. Used to be thought to be 7, but recently someone wrote a paper finding it was 8. Of course, if you consider the unwashed masses like myself who are not mathematicians, maybe we have Erdős numbers of infinity.
Walter Heyman, Erdős number 2. I would like just to modify a little bit what you said about his personality, because I don't think people stayed with him merely because they did mathematical theorems with him. I mean, I never proved a theorem with him, but I saw a lot of him. And I'm not sure the Erdős did much in the way of proving theorems with him. He was a very lovable person in many ways. All right, he was very irritating.
Yes.
And a lot of wives felt that. I mean, what you said there is quite right. My own wife found it. But he could also be very generous, and he did take a real interest if anything went wrong with you.
Yes.
I mean, he was a a good person, a really good person. He wasn't one of these introverts who think of nobody but
Right.
themselves. He did think of other people and so on.
He was very concerned about people's health, the health of their kids. Yes, definitely. And there was one other interest he had, and that was politics. He did like to talk politics. He did read about politics. He was very interested. Having been kicked out of so many countries, politics meant a lot to him.
Paul, Siobhan, you mentioned that you have a passion for passionate people. What do you think drives passionate people? And was Paul's passion in some way related to his adverse circumstances in growing up?
I think passion to that extreme. I mean, it was obviously driven by avoiding some things. I mean, clearly, I know that more because I was a tournament chess player and gave it up at the age of 12 because that's all I did all day. And in a way it was, as much as I enjoyed it, it also avoided my doing all sorts of having a normal adolescence and things like that. So, I mean, I think it can be part of it, but not in all people by any means. I think a lot of passionate people who succeed in what they're doing, and usually they have to succeed or they would have dropped their passion, have childlike personalities in the sense that, and I don't mean that in a pejorative way, I mean it in the way that a child is completely open-minded to things. One of what made him very successful is he could meet a mathematician and know nothing about the field in which the person did their work. And he'd say, "What are you working on?" The person would explain the problem. Paul would then have to interrupt him and ask, all definitions of terms and all these things because it was really unfamiliar to him. Once he understood it, then he would often come up with a solution very quickly. And it would be a simple solution. And you would think, why didn't people who have been spending their days working in this, who are the real experts, find it? Well, the reason they didn't find it is because he, found something out of left field, something that was so different. I mean, most of us who are successful, fall into a rut. We do the same kind of thing again and again. He was someone who was always jumping around, and I think that's very important to passion, particularly successful passion, is to be able to have that kind of open-mindedness that most of us don't have.
Philip Lee, did he prioritize the mathematical problems that he solved at all?
Did he prioritize them? In the sense that he knocked the ones off that he thought were the easiest to do, because then you were done with another page in God's book. And he prioritized them by the monetary values he assigned to the unsolved ones. If it were $3, it meant he thought someone was going to solve it. If it was 3,000, it meant he didn't think it was going to be solved in his lifetime. So yes, he did. Someone once asked him, because he had no money, well, Paul, what if tomorrow all your problems are solved? How are you going to be able to pay up? And he said, well, what if tomorrow everybody goes to the Bank of England and demands their money? He said, it's more likely that everybody will go tomorrow to the Bank of England and demand their money than it is that all my problems will be solved tomorrow.
David Wallace, you seem to imply that he was a mathematical nomad, as it were, from a very early stage in his mathematical career. Was his reputation established very, very early on so that in fact he could survive, or was it quite difficult?
Well, it was. Even when he went in 1934, so he's 21, that's when he went for his postdoctoral fellowship in Manchester for 4 years, he rarely slept in the same bed for more than one night in a row. He went all around the UK to different universities. People wrote about that at the time, that it was impossible to track him down. You never knew where he was. I mean, he went to every university practically that existed here then in search of what people were doing. So it was established early on. Then once the world opened up after the Cold War, he could do his 20, and I literally mean 25 countries, because I counted them all. And I was going to do a graph in my book of just charting back and forth between all these places, but confining it to one page of the book, you wouldn't be able to read it because everything would crisscross too much.
How far did Erdős get with the gold bar conjecture?
It's a good question. I don't know. He certainly gave up on it early on because he thought it was too difficult. It's something he returned to a few times, but he told me he didn't have any particular insights into it, so that he stopped.
Well, thank you very much for most lively answers to the questions, Paul. And I think it's been a really interesting lecture. Could you then show your appreciation of Paul?
I usually always wear a T-shirt, but I thought in a place that dates to 1660, I at least had to wear something over it. But this is the coveted Paul Erdős T-shirt. You can see him on the front. And on the back, you can see the way he signed his name. It started with PGOM, which stood for Poor Great Old Man. And that's what he put after his name just before, in the early 60s. Then he started adding other initials like LD for Living Dead, AD for archaeological discovery, then another LD for legally dead, and then CD for counts dead. But you can find these at eBay, and they go for a lot of money. Thank you very much.